Hello and welcome back to a new video in my C++ tutorial series. Last video we have implemented our first C source code and we compiled it and everything worked. We got an output hello world, which is exactly what we have written in here. Just to quickly recap, we have created a so-called function called main. The main is a special keyword which is detected by the Microsoft Toolchain when it takes our C file and makes a exe out of it, and then it automatically knows, okay, main is the thing where I want to start executing the program. Inside of main we have called two times the function printf, one time with hello and one time with space word and exclamation mark, and it all went fine, and we outputted hello world to the screen, and it was all nice. Today in this video you would now expect me to go on and show you how you can do more amazing stuff, but no, today we're not gonna do this. Today we're gonna actually do something different. Today I'm gonna discuss with you how the toolchain works. So how does all the Microsoft tools come together to take the C source file and create a binary exe out of it. So we're gonna discuss all these steps, and additionally we're gonna come to one issue that we had in our code, one big mistake that we made that works today but is very unstable. So it depends on like how you run the compiler, how you open up the command prompt, because I actually found out I always use the Windows terminal, which worked fine, but I also found out that when you're using what I recommended, the developer command prompt, if I take the developer command prompt, go to that directory by typing, no, not cd, cl, cd, that path, so cd and the path, then you are there. And then if you write cl, simple c app.c, you can actually see that we get an error here. Error LNK 2019. So you can actually see that the developer command prompt does not work. However, the terminal, if you're opening up Windows Terminal and use the developer command prompt from the Windows Terminal, it works. So for example, if I open up Terminal, go to the developer command prompt for VS 2022, which is, you should argue, the same thing that we have open here, but it seems like it's not, because if I go in here, go to that path and type in cl simple c app.c, you can see it works out without issues. The same thing if I would go, for example, for the developer PowerShell. Let's try that out. Developer PowerShell for Visual Studio 2022. Does that work? Let's see. cd to that directory, cl simple c app.c. Okay, that doesn't work as well. Does the PowerShell from within here works? So here we go to cd, cl simple c app.c, works. So somehow all of these native Windows doesn't work. The Windows Terminal works. If you don't have the Windows Terminal and you were getting the issue here, you can actually go in and search for x64 native tools command prompt. I've tested it out. This native one, this how is it telling that here? This native tool command prompt for VS 2022. If you could use that one, simple c app.c, that one works. So if you don't have the terminal, this is the prompt you want to go for. But this is really odd. So you can basically see sometimes it fails, sometimes it doesn't fail, and it is really a big mess. So there is some issue in our code because it does not work every time. And today we're going to get to the point why it fails. It has something to do with the behavior of C++, and that C also tries, in the default Microsoft environment, tries to run or to be compiled like C++, and some default setup that is like, it seems like not done here in the terminal, why ever. But yeah, we're just going to stick to the method that works for us for now until we get to the issue where we had the bug, and then we're going to fix that issue, and well, we're going to see that it works with a charm in each of these environments. So that's what we're going to do today. Alright, so how are we now getting from a int main printf to a .exe application that we can run? You can see it just opened the window and directly closed. We didn't saw this last time. Or better to say simple c app.exe here, hello world. How do we get from the source code that is human readable, like that here, just a file, 4 lines, very simple, readable, understandable. How are we getting from one of the simple file, which is 1 kilobyte big, to a exe file that is 121 kilobytes big? And well, if I would open this with Visual Studio Code, which is probably yell at me that it didn't want to open this up. But if I would open this up, looks like garbage, right? If I open this up, it really looks trash. How can we get to something like that? By just applying a such nice, innocent, readable text file. How is it possible that we get all of it out of that? How does it work? It's actually not that complicated, actually. Let's start by closing our Visual Studio Code because we really don't care what's going on here. We basically just care how we get to that. Well, as you can see, we have 3 files in here. We have our simple C app, our exe, and our obj file. 2 of them are very easy. The C file, this is our source code. We have written our instructions in here, what the application should do, our code. And second, we have the .exe file, which is also straightforward. It's an application. We can copy it around, give it to friends, and they can execute it, and they're always going to get the hello world message, just as intended by us, the developer. But what is that object file? It's really not something that we want to use. Can we double-click it? What is it going to suggest us? It's not doing anything. Double-click? No. Doesn't seem like it wants to open that file. It's called an object file. OBJ, not really something that we like, or is it? Well, let's try open this up. Let's open this up with the Notepad, our trusty, rusty text editor, and yeah, same story than the exe file. Some odd data is in here, but is it actually that odd? If you have taken a close look, you can actually see that you saw our hello world somewhere down here. But this hello world is kind of like surrounded by very obfuscated, not readable binary data. So these special symbols are like these question marks, these adds, and all of the things that these for example, also these Ys with the points on top of that. I like to call them U because in Germany we have like the U, like the this character U, and we have the same character with like the double points, and it is U and Ü, and we also have this Y, which is Y, so I like to call it Y, but that's just a little joke of myself. Yeah, this is just a little joke, but yeah, it's totally out of point. But yeah, this is basically telling us that this is binary data, because this is a special magic value that Microsoft really likes to use, this Y, this Y with double points on top of it. I'm gonna just call it U from now on. It's just a running gag. Let's see how many videos it takes until people forget it, and when I say it, they ask, what the hell is that? U and Y is that? U and EU. Yeah, whatever. Yeah, it's just some binary data. Basically, these are magic values, and they are representing some binary types. Okay, but that's not really the point of today. So how are we getting to that? Well, as you can see, obviously, we have 3 files named the same, but have different extensions. One of them was our source file, and one of them was our final output file. So it is really close that one is like an intermediate file, which kind of like stands in between the simple C app and the simple capp.obj. And that's actually correct. I'm going to show you something. I'm going to show you something by creating a new file. I'm going to now create a new text document, and I'm going to call this I do something.c. I do sdh.c. And yes, I want to change the extension. Let's now open this up as well with our Notepad. And now we have I do something.c and simple capp.c. Let's maybe shave them a bit down so that I can have them open up side by side. Alright, so what I want to do is I want to write a new function in I do something.c. You don't need to follow this step by step. And I want to basically write something like void greet. And then I do this the same then in the main function. The main we had, let's zoom in here as well. In the main we had this int main brackets, and now I have this void greet brackets. You again don't care about what that is for now. But basically what I'm going to do, I'm going to define a new functionality called greet. And this functionality greet should do something. It should, now I'm again in my OBS window because it's on my primary screen, lol. Okay, so this function greet should greet somebody. And what I want to basically do is I want to take away my hello world stuff, and I want to put this into this greet function. And now instead of here in the main, instead of calling this printf, I'm going to call greet. And now we basically would say, yeah, that's nice and easy, but we have 2 files. How can we do that? Well, it's actually quite simple. If I would now do cl simple capp.c, you will get an issue that I forgot a semicolon. Oh yeah, that's right. You need to have it there. Okay. But if I would now execute this, you can see that it now gets an error again. It now says unresolved external symbol greet, reference in function main. And that's true, because we have just moved out this greet from the simple C app to my idosomething.c. But CL is not aware of idosomething.c. And basically what we need to tell the CL application that we also want to use that. So I also want to use idosomething.c. And if I run this, we don't get any issue, and it seems nice. You can also see that here now it's also listing two C files, simple capp.c, idosomething.c, and it's also listing simple capp.obj and idosomething.obj. And if we would now take a look at our folder, you can now actually see that we have two obj files, but still just one exe file. So you can see that we have the idosomething.c, simple capp.c, and each of these C files has an associated object file. So idosomething.obj and simple capp.obj. So you can kind of like see that each C file gets an obj file. And then in the final step, it seems like that these two obj files have been merged together in one simple exe file. And to check that this is true, we simply just executed simple capp.exe, and we still get our hello world. So even though the hello world is now in a complete different C file, it still works in the same exe. And this is the full idea of C and having multiple source files. We're going to get to that in a full depth explanation in the future. How this works with multiple source files, how you properly do this, because like how we did it, it's not good. We haven't done this nicely. But we're going to get to that in today and then in a few videos again when we talk about really doing multiple source files. But the point is basically to show you that each C file gets so-called compiled, because if we take a look at this, Microsoft optimizing compiler, it gets compiled to an individual object file. So everything that is in idosomething.c, all the text that we have written in there has been compiled to one object file. And the action of compiling means that it gets translated from the English C language. So C is kind of like English. I'm going to say it's English, printf, main. Later on we're going to have if, while. This is like all a English syntax that wraps around the constructs of the languages. And basically what the compiler does, it reads our source file, so our simple capp.c and our idosomething.c, and it starts reading this line by line from top to bottom, and it checks what's in there and translates this to so-called instructions. An instruction is a native command that the computer can execute. So the computer, the CPU, is a hardware, it's an electrical device, and this electrical device has several functionalities built in. So for example, it can do addition, it can do subtraction, it can execute code at a certain point, it can jump around in code, and basically it has these hardware functionalities that it can do, the so-called instruction set, x64 instruction set, with all the extensions that you might know. For example, like games, they are always talking about vector extensions or SSE instructions. And if you had an old computer, it might be that you want to start a game and it says, hey, this game can't run because your system does not support SSE or SEMID, and then SIMIT, and then basically a version number. And basically this is a hardware, the CPU is a hardware that can do several tasks like doing math. Mainly it does math. It does all the math operations you might imagine. And also like storing memory, storing data, reading data. So it does a hell of a lot of things, that CPU. And what a compiler does, it takes this textual representation and it translates this into the native commands of the CPU. So the compiler basically knows how the CPU works, how the x64 instructions work, and they take your code that you have written in here and it transforms this into raw machine instructions. And well, then it's done. Then we have some binary data that we could execute. Wrong. It's not how this works. So if we would just have binary, then we would basically already have two binary executable object files. But these object files are not executable. I cannot click them. idosomething does not print something, and executing this does also nothing. Why is that? Well, because C projects are quite complicated, and also C++ projects. So they have decided to treat each C file separately. So the compiler always takes a look at C files. So every C file is compiled. And and every C file is read from top to bottom. But can we do something if we read main from top to bottom? Actually, no. Well, of course, we know that main starts and calls greet. So we can kind of like do an instruction, like for example, say, hey, I do something like main, and main is basically call greet. This is basically how it would look like in very simplified assembler code. And after that, it would call something like red to return. But before it would do something like XOR, EX. It would do something like that, but it's really not crucial that you understand this, but not even sure if this is correct with EAX. It could be anything else here. But basically what the compiler does, it transforms that into that, but in a machine format. And what it also does here at the I do something, it does something similar here. It basically says, okay, greet is gonna be, it's gonna do something. I'm not gonna go into depth what it's doing here because I would not be even able to do this just out of nowhere. I would need to take a look at assembler again to see what's going on there. But it would do something like that. It would basically do something like that. So this is basically what the compiler would do, and then it would spill out this as binary information. But does this help something? Is greet something that the computer is aware of? No. Greet is nothing the computer is aware of. Main is nothing that the computer, the CPU, is aware of. The CPU is not aware of main. The CPU is not aware of greet, and the CPU is also not aware of printf. So by just compiling these files and putting them into a machine-readable format, we're basically not getting very far, because the computer does not know what main is, what greet is, what printf is, or what greet is. It knows what call is. It knows call means call something else, but it doesn't know what or where greet is. It knows what XOR is, it knows what red is, it knows what mof is, it knows what call is, it knows what red is. So it knows all of that. But it does not know what greet is, and it does not know what printf is, and it does not know what main is, and it does not know what greet is here. These are basically some definitions. So basically this main indicates, hey, here's the code for main. And this greet indicates here's the code for greet. And now we are getting to something, because basically what we have inside of our inside of our simple capp.obj, we have a block that is called main. So basically inside of the simple capp.obj, there is an information that, hey, the following code is for main. And the same is in the I do something.obj. In the I do something.obj, we have a block that says, hey, here is the code for greet. So here you go. And now if you would take a look at the obj file from simple capp.c and I do something.c, you're going to get one thing that is very important. You can see basically in the simple capp.obj, there is a reference to greet. So I have a reference that I want to call greet, but I don't know what greet is. And then I do something .obj, we have something that is called greet, an implementation for greet. And now is where the second step of the compilation process comes in, the so-called linker. What the linker does is it takes all of your object files that were already there and tries to merge them into one single executable. And how does it do that? Well, first of all, it searches for a keyword called main, because main is the entry point, and there everything should start. So the linker searches all of your two files here, all of these two obj files, for a main file, for a main label. And here it basically says, here I found my main label. Okay, so now I'm going to put this to the start of the application. So I'm basically replacing this main for app start, something like that. It's going to be a bit more different, but basically inside of our simple capp.exe, we would have something like app start, and it would paste in that call greet. Now the next step is, because it just pasted in our main things, it would basically try to read this, and it basically sees, oh great, I have a greet in here, but I don't know what greet is. So it goes on and looks back at the object file. So it tries to search in the simple capp.obj for a greet, but it cannot find it. Then it goes to the I do something.obj and it says, oh, I found a greet. Great. So it basically takes the binary code, like the instructions, the raw CPU data that was needed for greet, it takes them from the obj file and moves them in the exe file. So maybe somewhere down here, and it basically now going to get something like, let's maybe call this function greet. And basically it's gonna be look something like that, so it's gonna have an address. And now what it can do, it can basically resolve that because it just pasted in greet, so it can go back up to the simple C app, and now it knows, all right, I want to call greet, but now I have basically seen where greet is, so I'm gonna say call that one, and that one is a so-called address. You don't need to understand what it is. It basically is a offset that is only relevant in your exe file, and it can basically replace this and link this down to the code that you have implemented in a complete different source file. And that is why it's called linker, because it takes all of your obj files, all of your functions, your references that you had, it takes them all together in one simple exe file and links all of these open references that the compiler was not aware of, links them together so that you can execute them at runtime. Next step here would be that it basically sees that printf, and now it would try to find the printf. And now we have an issue because printf was never defined here. We only use it, but we have never defined it. So now we have a big issue. Well, kind of true, but actually not. The thing is, printf is coming from the so-called standard library, C standard library, and this means that it is already supplied by Microsoft. So inside of the toolchain, inside of your folder where you installed the compiler, there is a static library. It's called static library, and inside of the static library, it's similar to an object file. There is basically this printf function, and then it would basically copy that printf, let's say, to something like here, and let's just put in some points here so you kind of like get the point. Basically copied the printf from the standard library, and it basically pastes the references in here, and then everything is nicely resolved and linked. It's getting unpacked binary and spilled out into the exe file. So this is basically how the process works. And now you can basically also see why we have these two obj files associated with two source files and one simple exe file. And you can also see like why the exe file is so much bigger, because of course you're gonna need way more code than what we have written in here. Printf is actually not very innocent than it looks. It looks very innocent, it just takes in the simple argument, it just prints to the screen, right? No, there's so much more code associated. All of this creation of a command line, printing to the command line, calling the Windows function, allocating the memory for the command line, opening the command line, having the window of the command line managed by Microsoft Windows, have the window destroyed when the application exits. This is like all required inside of the application of the exe file, and this is why this exe file is so much bigger than what we had here. Because, well, this is just some opening dangling reference to printf, this is just an opening dangling reference to greet, and all of these opening dangling references are going to merge together into this binary exe file and link together. So simple capp.obj is linked to the idosomething.obj because we are using this greet function, and the greet function is basically, so this idosomething.obj is basically linked to the Microsoft library, the standard library from C, and actually there is a standard, a C standard, which basically says, okay, if your compiler is compliant with a certain C version, you must support the following functions to basically allow all these standard features to work and make C portable. So basically Microsoft is kind of like forced to implement a few features of C as always. So it's really important that they do it. If they don't do it, they are not compliant with C and nobody would use the compiler. Yeah, in theory, at least. So just to recap, I have prepared a diagram how this works, and there's a bit more information in the diagram, which we're going to get to step by step. We're going to start here, of course, today very simple. We're going to get more involved step by step. So just to recap, because it's a bit bigger, this is how it works. So the input was our source code.c file up here at the top of the diagram. Down here at the bottom, we have the executable machine code, the exe. That is also what we know. And we also know the obj file, the machine code, which is before this step called linking. But as you can see, the compiling, what I just always called as the compiler, are actually 3 steps that are done, but all of these 3 steps are done by the compiler. It's not entirely true, because like the subsystems of the compiler are called preprocessor, compiler, and assembler, and they are in fact different systems that could operate independently, but we are going to always use them in one step, so we don't really care what they individually do. I already told you it's reading, the compiler is reading the C file line by line and basically transforms this into binary data that we cannot understand, but the computer can understand. But this binary data, this obj file, has open and dangling references that are basically going to nowhere. and that OBJ file and the linker make sure that all of the data is merged in together correctly, so every reference is resolved and every reference exists inside of our machine code executable, our exe. And of course, there's also like the stuff done, like adding the information so that Microsoft can actually run the application. So there's a bit more involved in the linker, but by the fact, it's basically just taking all of your object files, all your machine code that was just dumbass compiled, and links them together and tries to link them together with the standard library. And this is also why we get the error when we previously, like if I could redo this, where we had basically just a print. This just print was basically an open reference, and the linker was not able to resolve that reference because there is no function print defined by default, and so we got this unresolved external symbol print reference the function greet. So this is basically what the linker does. If I would have a syntax error like removing the semicolon, then you can see the compiler jumps in because the compiler cannot parse this to valid machine code because the C syntax is not valid. So the compiler just transforming all your code into machine code, and the linker then goes in and tries to link this everything together and produces your exe file. Right now, very simple. But there's one thing that we need to understand additionally. We need to understand one more tool, the so-called preprocessor. This is going to be a quick one. The preprocessor is, de facto, basically just a copy-paste tool. The only thing the preprocessor does is copy-paste stuff around, replaces stuff in your source file, and acts like a so-called nice little tool that preprocesses your source code to basically transform it into the version that is then supplied to the compiler. This doesn't mean that it's really copy and pasting, inserting and replacing in your real file. Your file is always going to be staying the same. The C file is always as you type it in. No tool, nothing in your toolchain is going to modify your C file, or not directly the file on disk. But if I would use the preprocessor, like I could say to the preprocessor, just a very quick one, I could say I want to define hello as hello, like similar than here. So we have basically this hello here, and now we have that hello. And basically by doing this like that, we basically tell the compiler that we want to replace hello, everything in caps. This is like a convention that you do if you do this search and replace with the preprocessor. Basically everything with hashtag means preprocessor, defines means kind of like search and replace. Hello means this is like the search. I want to search for hello, and I want to replace it with, in quotation marks, hello, without caps. And from now on, so it's only affecting everything that comes below of it. So it's not going to replace something that is on top of it, only something that is below. And it would basically now go in, and while it's basically parsing all these lines, it will see, okay, I see an hello, so I'm going to take this hello from up here and paste it in there. This is a really dumb example, but we're going to get to it when we want to use something like that in the future, when we have a bit more examples. So yeah, this is like one of the cases that you use the preprocessor for. There are also more options, like you can basically control the compiler and linker by having preprocessor commands. There are special Microsoft commands that basically are addressing the compiler and linker, and basically you could basically say the linker or the compiler, they can give you warnings if you do something wrong, and you can actually with preprocessor macros say, hey, for this block of code that is now coming, I want to disable that warning, and the compiler would not spill out that warning for that specific section of code. So you have many options available with the preprocessor as well. Another thing the preprocessor is used, it is used for copy and pasting the contents of files. So what I could do basically in here, I could go in and say I want to include a file. So I want to basically include the content of idosomething.c, and I could say include idosomething.c here, and what the preprocessor would now do basically, it would basically see, all right, I want to include something, I have normal quotation marks, which means search in the current directory. In the current directory, it's going to find that file called idosomething.c, so it's going to take out everything that's in that file and paste it there. Of course, again, not physically in the file, it is doing this in a like virtual file before it spills it out to the like real compiler. But let's put this back again so that you can actually see what the hell? Why is Control-Z not working in that bullshit here? Now I need to write my main again. Ah, great. Hashtag include ido. We really need to switch to a good text editor, but damn it, this is the last video we're gonna use Notepad. From now on, we're gonna use a correct, proper IDE, but let's quickly fix that up again. No, that one. All right, so great. Okay, so of course, great, like that. So I could do this like that and would have, you would think that it has the same effect, but does it really has? Let's try it out. Let's clear this again and let's run this. And well, now we have an issue again. Now we have a problem because, well, let me quickly explain what happened. So what does the issue is? Do we have a compile error? No, both of our C files compiled correctly. So the C file was correct. Let's assert this by taking a look at this. So this is just defining greet. What is this doing? Well, it's including greet, and it's including and defining greet, by that way, and it's defining main. Okay, so this is actually correct. We have two valid source files here. But now the linker comes in. Greet already defined and simple c-app.obj. So what does the linker do? Well, the linker first starts with that file here. It sees, alright, there is the void greet, there is the int main, I have these two functions. Then it continues on, and it now basically reads the void greet again, because it's also in the I do something.obj. So now we basically have a void greet in the simple c-app.obj and in the I do something.obj. And if we have 2 times the same functionality defined, so 2 times the same function defined, the linker is not really happy with that, and it says it is already defined, that greet is already defined. So that's not really the thing how you would use it. How could we solve that? Well, we could just simply solve that by removing the I do something.c from the compilation. And if we do it like that, it works, of course. But that's not really the point. It's not really the point to include C files, but we're going to get to that later. Okay, of course it's now working because I changed this, but if I would do this like that, I do something.c, if I would put this to that, and try this out again, works, right? Because now we are no longer including the I do something.obj, we are not even compiling the I do something.obj, and then it works again like a charm. But yeah, that's not really the point. What I want to show you is basically something different. Okay, so let's do this again with the correct one, and it again works. All right, so very nice. So now we have basically just discovered how helpful the preprocessor is to do stuff. All right, so now we're going to get to the issue that we have with our code. How can we actually see that we have an issue? Well, it compiles and it worked, but, well, it does not really work. You saw earlier that in the several command prompts we had issues. And these issues are because we are not really using the correct printf. We are just like depending on a simple call printf, and we really need to hope that Microsoft called the printf function printf. And it seems like that in some versions of the developer command prompt it works, and in other versions of the command prompt it does not work. Well, why is that? Because the function does not really need to be called printf. The fact the C standard only says that printf needs to work. So printf, you need to be able to compile your code with that word printf. But you don't need to compile your code printf like that. So it's not really required that you use printf here. You can basically use printf however you like. And it's not even guaranteed Microsoft calls this printf. They can call these functions whatever they want. They just need to have a way that printf leads to these functions. And I told you that we could like use this preprocessor like this, define hello to hello. But we also can abuse this preprocessor whole differently. We could basically say printf is msvc implementation of printf. Right? We could do this like that, which basically would replace all occurrences of printf by this __ msvc for Microsoft Visual C _ implementation _ of printf. We really don't know how Microsoft called the actual function, because Microsoft really loves to call them differently, like also with message boxes on Windows. If you want to opening up a Windows function, there are most of the time 2 implementations of the function, one for, it's a bit too hard for now, but basically Microsoft has for its own Windows functions that only work on Windows, they have most of the time at least 2 implementations, and depending on how you are building your application, one of these 2 implementations is going to be selected if you don't explicitly select one. And it's always also probably like that with printf. And We had luck that our command prompt that we opened up were able to link this together, but this is not guaranteed, and this is going to fail as soon as we switch to C++, because C++ does some additional checking. The C compiler just sees the printf with a string in here, and it says, all right, I want to use printf with a string, I'm going to assume it's there. The C++ compiler is not that flexible. The C++ compiler basically sees printf with a string. I'm not aware of a printf with a string. I'm going to fail. And that is what we want to see now. Let me quickly close these two files. Let's go in here, and now let's rename them. I'm just going to rename them from C to CPP, both of these files. C, CPP, okay. Can also now delete the object files to make sure that we are here clean. And now we have two files. I do something.cpp and I do something.c. Simple capp.cpp, sorry. Basically two source files. Now they are no longer called .c, now they are called .cpp. And does it make a difference for the file itself? No, it's still just a text file with everything that we have written in here. Now I have them the other way around, which is not good for you. I'm gonna have this consistent, there we go. So the files are still the same, but they have a different ending. But this ending is a magic ending, because as soon as we are now gonna say compile, if I now would, maybe let's see, I think I cleared them already out there, yeah. But if I would now go and say cl like we did it before, like cl simple capp.c and I do something.c, it's no longer working. It's saying that simple capp.c, no such file or directory, cannot open source file. So it was not able to open simple capp or I do something.c, which is very logical because we renamed them to CPP. So we also need to rename them here. So simple capp.cpp and I do something.cpp. Let's start this. Okay. Did not work. Did not work at all. We got three issues. One issue in simple capp.c. In simple capp.c at line 3, we had the error C3861. This is just a number that represents its error. Basically, C3861 represents the error identifier not found. And what it now basically tells us is that the identifier greet has not been found. The same here in the I do something.cpp. At line 3 and line 4, it says C3861 printf identifier not found. Printf identifier not found. So to recap this on the file, it didn't find the greet. It didn't find the printf. Well, why is that? Because we are basically not having it. Inside of the main, as I already told you, the compiler is only aware of the current source file it's evaluating. It reads int main. Okay, it knows by writing int main that an int main is in existence. Then we have these open curly brackets and close curly brackets, which means, okay, I'm going to supply an implementation to that function main. And inside of this function main, I want to call a function greet. But now the compiler has an issue with that because greet is defined nowhere. So it's not defined. It's not defined in the current context. It's defined here. But the compiler is not aware of that. Well, I could go the brute force way and include this here and say, yeah, just include that here. But then we would get the same error again that we had previously, that we have multiple symbols defined. So I want to do this the proper way. How can I do this the proper way? Well, I basically can tell the compiler that the printf, that the function greet is in existence. So I can basically tell the compiler, okay, I want to have a void greet, just the same that we had it here, completely the same, but without an implementation, just with a semicolon. Tells the compiler, hey, this is how greet looks, and it is there, but you don't know about it, but it's there. And by having this like that, if I would do this now, we would no longer have an error with our simple capp.cpp because we have basically told the compiler, hey, there is an existence of that function. And now the compiler behaves the same then on a C implementation, and it basically says, oh great, there is an implementation. I'm going to link to that later. I'm going to leave everything else to the linker. Alright, so now we would be tempted to do the same thing here with printf, and well, how does printf look? Well, let's do a quick search on the internet, and we can find, if we type in printf Microsoft, we basically find that file here, the Microsoft documentation for printf, and you can basically see how Microsoft defines printf, and we can just plainly copy this, just very blindly copy and paste it over here, and hope that it works. Does it work? Well, it looks ugly. It does not seem that it worked at all. This looks really bad what we got now, but it's actually not that bad because I know what's going on. Basically, they have, in the documentation, Microsoft always have this a bit fancier than it is in real life. So if I would now maybe make this a bit less fancy than the documentation and save this and run this again, it works. The compiler has nothing to complain. The compiler was compiling simple capp.c, I do something.cpp, and it was all good. Until the linker jumped in. Unresolved external symbol printf. Referenced in function greet. You can see that these functions are now looking completely different than what we had before, like this int, c, decal, printf, const char, print, add, h, p, e, b, d, z, z, whatever. This is just fancy because it's C++, and in C++ functions are way more extensive use than in C, and because of that, basically the functions have these obfuscated names, and basically the name here is indicating what arguments are used, but I'm gonna get to that later. And this is basically a textual representation. So the Microsoft function is not called print. Even Microsoft says it called print. The thing is, as I already told you, Microsoft has many implementations based on how you are compiling your application of that same print function, and we cannot just plainly use this here. If we plainly use this here, it's not going to work, and I can tell you we are not going to get this to work like that. So we need to use something different. Remove that. That didn't get us far. So, well, how can we solve that? Well, let's go back to the documentation and let's start a bit reading down here what's in here. So, okay, format control, optional arguments, local to use, not really what we want to do. Return value, we don't care about that. Remarks, we don't really care about what they want to remark us to do. We care about that section down here, requirements. What are the requirements for using that printf function? So, routine function printf. And you can see that we have a requirement here. It's called the required header, and to use a printf function we need the header stdio.h. So what is that header? What isn't header at all? Well, a header is just a text file, and a header only contains such things. So something like that, basically defining, well, there is something read and it looks like that. This is basically an implementation that you would find in a header. This thing that I just plainly have written into our main file. And this is something that you would have in a header that basically tells the compiler, hey, the functions in stdc, stdio look like that. Basically telling the compiler, IO functions look like that, printf looks like that, printf can look like that, there's this special function of printf, and they are looking like that. Basically what we had here, but for other functions. So, well, where do we find this stdio.h? Well, it is somewhere in the Windows Kits folder, not kits, yeah. Basically, if I would go to quick access, I already prepared this here. It is in, let's expand this a bit, local disk C, program files x68, Windows Kits, 10 include 10.0.19041.0/ucrt. If I would open this file location up, you can see that there are many files in here that are called .h. And there's also this stdio.h. And if I would open this stdio.h with the notepad, you would get a hell of a lot of Microsoft code here. And if I would now Control F in here for printf, you can see that we find printf. Here is a printf function. If I would go down, I wonder if I'm gonna find a hell of a lot of printf. Let's open the brackets. There are so many printf functions. For example, like here, that stdio, common, vf, printf. Like Microsoft has many implementations of that. And well, one of them is the right one for ourselves. Now we could now try to find the correct one in that file, but I'm gonna tell you, even if you find something that looks close, it's not gonna work. Because there are so many things around that it's really a pain in the butt. Now, you could argue and say, yeah, let's just copy that full file. Control A, Control Z, go back to my I do something.cpp, paste it in, save that, compile, and it works. You can do simple capp.exe, and it works. But no, that's not really what we want. We don't want to paste the full Microsoft file in that file in here. We basically don't want to paste them ourselves, and what I already told you, we have a nice little tool that can copy-paste files for us, and it is called the Preprocessor, and we already used it with #include. But what do we want to include now? Well, now we want to include the stdio .h. And as you saw in the Microsoft documentation, we have these pointy, sharp brackets here. So these greater, smaller symbols, this stdio.h and these greater and smaller symbols. And these symbols just act like a normal quotation mark. But a normal quotation mark, as I already told you, means search in the current directory, while these sharp brackets are basically meaning search in the so-called compiler include path. By default, the compiler is always going to have several directories where it's going to search its include files. And within these directories is the standard library, the Microsoft standard library. And inside the Microsoft standard library, we can find this stdio.h. So this stdio.h is basically inside of our include path, and by using these sharp brackets with the greater and smaller symbols, we basically tell the compiler to search on the default path, and we basically say it, include everything from stdio.h. And now, if I would go back to my command line and do it again, it still works like a charm, can execute the application, still prints hello world, and it works very, very nicely. Well, that's how it goes. Very, very simple. Well, let's now merge them back together because I don't want to have my I do something.cpp. This was just to show a bit of what's going on here. So let's now merge them all back together. Let's close this all up. Let's go back to our initial folder, one back. Let's delete the object files. Let's delete the I do something.cpp. Let's also delete the exe file. And let's rename the file back to the .c file so that we are back at our good old innocent C application that we're going to stick with for the next videos until we get to a bit more advanced stuff where we're going to go a bit again and revisit how that works with external files. But, well, to summarize, I hope it was a bit clear today and clear enough to understand. We have all these steps involved to basically generate a normal C application. And of course, if we try to CL this again, it's of course going to work because the hashtag include, it's not a C++ only thing. It also works in C, and it is also good practice that you're going to use it in C. And now I'm going to tell you something. If we now take the defunct developer command prompt that didn't work earlier on, if I take that one now, get my path back, maybe delete this very quickly, that you see that we really produce an output, cd to that, and cl the simple capp.c, you are going to see that we no longer get an issue from within the developer command prompt, not only from the terminal. And if I would now do this, simple capp.exe, we would also get our hello world output. So now you can basically see we made our application stable. It will now, this one is guaranteed to run everywhere. No matter where. Everything that can in the C can do this. Linux, Windows, OS X, whatever you want to do. Every operating system supporting supporting C, and every C compiler should be able to read this. Without our include, as you can see, not even all the Microsoft tools know that. This is just how this works. It's a bit complicated, and I hope with that video I can make this a bit more clear. So basically, yeah, just to summarize again, simple capp.c, our C source file, going to be preprocessed by the preprocessor that looks at hashtag include or hashtag define or anything starting with a hashtag statements, and does copy and paste replacements in the file. Then the compiler jumps in, compiles your source file by basically taking a look at what functions are defined in here, so which functions get in source code associated. They translate everything that's in here to binary data, spill it out in an object file, which is then consumed by the linker. So one of your object files or any of your object files, how many you have, are going to be consumed by the linker, are going to be extended with the standard library, and external functions and references like printf or the greet that we had previously are basically now linked together by the linker and produces one big chunk of exe that can be executed on your system. Alright, so I hope that helped, and yeah, that's it for today. So thank you for watching. Make sure to like and subscribe, and we're gonna see us in the next video. Bye!